Welcome to qnawire.
The force applied by the spaceship puts a torque on the asteroid which changes its angular momentum. We assume that the rocket ship's direction is adjusted to always be tangential to the surface. Therefore, the torque is always perpendicular to the angular momentum and so will not change the magnitude of the angular momentum. So, the magnitude L of angular momentum L is a constant, but its direction changes. So like here, the direction changes by theta. So this is similar to the action of a centripetal force on an object in circular motion. So from this diagram, let's make an approximation for torque. So torque is dl over dt, where dl includes the change in the angular momentum both in magnitude and direction. So here let's take the approximation of dl to be del L over del T, and del L over here is L times del theta over del T. And del theta is basically theta now, the change in angle. But okay, so let's just keep it del theta over del T because this looks nice. Now from here we can say del T is equal to L over del theta over tau, and L, as we know, is I times omega, and tau is F times R times cosine of theta, where theta is the angle between F and R. Let's call it phi so we don't get confused between these two angles. Now, since force is tangential to the circle and R is towards the center, so these two are perpendicular. Therefore, cos phi is, sorry, this is sine phi because tau is cross product of f and r. So sine phi goes to 1 and therefore tau is equal to f times r. So that's what we are going to write here. Now, I for a sphere is equal to 2 by 5 mr square. Now we can simplify this equation. So we get 2 mr omega del theta over 5f. So the r and one of the r cancel out. Now let's plug the values that we are given for the problem into this equation. So let me just write the expression again. So we got del t to be equal to twice of mr omega del theta over 5f. Now we are given that the mass is 2.25 times 10 to the power 10 kg. R is given to be 123 meter. Force is given to be 265 Newton. Omega is given to be 4 revolutions per day, but we have to convert it into radians per second to get the time in seconds and also to be consistent with the units. So we have 1 revolution to be equal to 2 pi radians. So this is the numerator in radians, and in one day we have 86,400 seconds. and del theta is given to be 10 degree, but we also need to convert this into radians, so we have the same unit for omega and theta. So this is equal to 10 degree times 2 pi radian over 360 degree, because 360 degree comprises of 2 pi radians. Now we simply plug these 5 variables into this equation and solve it, and we will get this to be equal to 2.12 times 10 to the power 5 seconds. Now we can express this time in units of hour. So in hours, this will be equal to this value, and this is equal to 58.9 hours. So note that in the diagram of the book, the original angular momentum is upwards and the torque is into the page. So the planet's axis would actually tilt backwards into the plane of the paper and not rotate clockwise as shown in this figure.